Hi everyone, this is going to be a video about the change of variables for double integrals, and it's going to introduce the formula and analysis that is a little bit more rigorous than usual calculus textbook. So we're going to start with reviewing change of variable for polar coordinates. So this part here is some region in xy plane, and this is called a polar rectangular region, because if you look at polar coordinates, usually it's r theta, but we're going to be looking at the general st variable sooner or later. So I used SNT here. S serves as a radius r and t is the angle. So the usual polar coordinate here is a r cosine theta is supposed to be cosine theta, but I wrote it correctly here, and y is supposed to be r sine theta, but I'm using SNT. So this is actual region we are looking at in xy plane, but if you look at the situation for s variable and t variable, they're independent and varying from a certain range, not depending on each other. While s and t are related like this too freely, but under this transformation, and x and y range form like this. So this line here is a theta equals something, alpha for example, and this is another line where theta value is fixed and theta varies between here, and r is varying from here to there, the radius. So all this thing is summarized in this formula, and when we have this parameterization, that's the right word to use for later on. If you have a certain region and if you have a nice parameterization such that the parameters range is like in a rectangular shape like this, then integral, when we rewrite the integral in terms of this parameter, the integral becomes rectangular integral, for which integral is a slightly more convenient. So that's the whole point. So, and as an example, we learned this polar coordinate double integral formula. So here's how it usually goes, and this piece here is supposed to be a very small piece, and as we divide this polar region in the following way, and these arc here is where the radius r is fixed, and these rays that's coming out like this is the positions, a line where theta value is fixed. So by dividing it this way, which correspond to S and T line over there in an ST plane, then this creates these little pieces and cells, and by dividing this into by indexing along this r value and indexing along this theta value, we label those each pieces as a kjth cell. So this is going to be a kjth cell, and the area of this shape is going to be denoted by this delta AK. And I'm assuming here you have looked at this polar coordinate change of variable for double integral. So that AKJ, this is kind of typical polar region, and you look at area of a circular sector and subtract it by another area of the circular sector, and you arrive at this type of form that it's not approximate, that using the mean value theorem you can write down this area delta AKJ an exact form like this, where sk hat is in between sk minus 1 and sk plus 1. So we figured out how to write the area of this piece. Then the double integral requires the height over this region. To determine the height, we have a freedom of choose any points in that region. So that usually denoted by this star notation. So any point here has x and y coordinate for that kjth piece. So we denote it like this: x kj star, y kj star. So that's the free point we choose here. But the trick here is that sk hat is not a free point. This is a special value that makes this particular form exactly equal to this area we're looking at here. So since these are the free choices, if we make skj star and tkj star whatever, this tj here, tj is one of the endpoints of the interval along this t line, and sk hat is the special value. So if you choose sk star to be this sk hat, then the Riemann sum will be consistent and nice. So here's what I mean by that. Now sk star is not free point, it's a special point we have to choose to make these two things equal. Then skj star is chose to be this point. Now this is the double integral over that polar rectangular region, the region in xy plane. This xkj star and ykj star here is going to be substituted by the usual polar coordinate change of variable in polar coordinates. So that involves this r theta here. I'm using s and t. So s and t, whatever the choice we made there. So choice we made there is an sk star, j star to be this sk hat value. tkj star was an arbitrary choice. I made it here. Arbitrary specific choice, I made it here. Now what we have to be careful about is this delta akj. Delta akj appear here, and that's the formula right there. Instead of sk hat, we can use skj star because we made that skj star equal to sk hat there. So I adjusted it a little bit. So if you look at this part right here, everything is written in terms of skj star and tkj star. Even this extra part and stretch factor, how much the area is stretched as we try to describe it in terms of delta s and delta t there. There is this factor kicks in. Everything is in star notation. So you can easily conclude that from here, this continuous functions, f is continuous and all the way up here, can be easily written as a double integral in terms of s and t. And this rectangular region over which we're about to take this st integral is a rectangular region. So let me show you the picture again. So this was the picture. This original polar rectangular region has this bent shape, but if you change everything in terms of s and t, the way s and t varies relative to each other is completely independent like this. So integral we're taking is going to be a lot nicer, somewhat often more convenient. So the main goal usually is doing this change of variable, that we have this weird looking region and find some parametrization there and try to, straighten things up like this. So that's what happened here in this special shape polar rectangular region, and we could change the formula into this way. If it is a different type of a region, you don't expect the polar change of variable will give you a rectangular region like this. It has to be that particular polar rectangular region. So the main motivation I'm doing this business, which is usually well introduced in textbook, is I go slightly deeper to this analysis. So the following is the part that we're going to focus on. So exact calculation of delta akj is something we did. And for that we use this sk hat. First you formulate clearly using the circular arc area of the circular sector formula. Then, because it's a bit complicated, the difference of the two things, and we use mean value theorem to get a slightly different formulation using the special values of a different functions. So in general case, we have to pull something out like this. We can look at exact calculation and come up with a using the mean value theorem, a slightly different formulation from which the calculation becomes better. And so main focus is going to be getting this different formulation of the exact area. So before we get into this difficult or rigorous proof, let me show you some example how we're going to use this change of variable for double integral. For example, if you have this triangular region and if you're trying to integrate some two variable function over this triangular region, then typical thing is that you figure out the functions of this boundary and do the vertical integral or horizontal integrals, for all cases you have to divide it into two cases, and it's not absolutely necessary to rewrite this integral into different forms, but sometimes it's beneficial. So what we are trying to do here is that reparameterize absolutely this x and y are depending on each other in this region to describe this, and even given by different pieces when however you do it. So if you can reparameterize this one as a rectangular region, just like we did with our polar rectangles, and integral might be slightly more convenient to integrate. So here's the first step toward to the parameterization, and all this idea depends on the on the shape of this one. Because it's a triangular shape, the following method works. If it's different, and you have to use different ideas. For example, first thing we're going to do is we're going to parameterize this point along the boundary of this triangle. So we're looking at these 2 points. I call that vertex A, and that vertex B, and we try to find a position in between it here. Maybe you can interpret it as a position vector from O position there. So idea, we've looked at this before. The parametric equation of a line that passes through A and B, especially the line segment that starts in B or A and ends it there. Okay, that's something we practiced. The idea is that because it's a line, everything is given in terms of a linear function. The x and y coordinate is given by linear functions. So knowing that how the answer look like, you always write down the two vectors. I'm writing here as a column vector form because the formula for the change of variable uses the determinant. This is more natural to see where the determinant kicks in. So 1, 3, here is this vector I wrote, and 2, 1 is the position 2, 1, but I wrote it as a column vector 2, 1. Then there is going to be some linear factors involved in here. What we want to do is that, for example, when t equals 0, it's going to pick up this b, for example. T equals 0 will kill that 1, 3. So that's going to be 0 vector there. When t equals 0, this coefficient, scalar part, picks up 1, so that 2, 1 survives. So I did it backward. So this is a t equals 0, that 2, 1 survives there. When t equals 1, this 1 becomes 0, and that 1, 3 survives. So when t equals 1, 1, 3 survives right there. So t equals 0 is here, t equals 1 is there. So this position vector goes through these 2 points, and it must be straight line because they're degree 1. So we parameterize this one nicely. So what I actually did, and I explained why this one is a line, but this is quite clear to how to construct it every time you see these 2 points and think about constructing a line segment. Another thing is that no matter what this 1, 3, 2, 1 are, it's always a t equals 0 and t equals 1. For all cases of this line segment, t always varies in this way of parameterizing. T always varies from 0 to 1. So I kept that there, and 1 and 3. So this part here is the line that we already parameterize it. So we're supposed to parameterize not just the line here, but all the points inside this triangular region. So the idea is that all those points inside the region is kind of connected to the 1 points on that opposite side. So if you have one position, by shrinking that position vector we calculated before, you can kind of reach any position in this line right there. So if I scale that earlier vector, let me show you, earlier vector is here, t and 1 minus t, 1, 3 and 2, 1 there. If I rescale this one by a certain parameter s, let's say, so that's why s and s is multiplied to the whole expression here, then when s equals 1, it's going to be exactly that point. You can see s equals 1 and s equals 1. And when s is 1/2, this is going to shrink all the way to the half position of this entire length. When s equals 0, then it's going to shrink all the way down to 0. So by choosing any point in here, which is parameterized by t between 0 and 1, and then by playing with this S, you can reach anywhere in this triangle. So you're looking at this picture, it's clear that we parameterize it, except that position right there, everything is quite nicely parameterized. So there's some collapse going on, but that does not affect the volume of anything. So this is acceptable parameterization for change of variable of double integrals. So let me show you how this one simplifies together. So this first column, first spot of this column vector is x coordinate, and that's the y coordinate. So st and negative 2st together makes a negative st. All right, and then there's a 2s. So if you look at all the x component and y component, it simplifies to this one. Okay, you might pause the video and do this type of calculation by yourself. But after you do that, it arrives in that shape. Again, the way we parameterize it is t equals 0 to 1, and s from 0 to 1 will shrink this each of the position vector with endpoints on that line AB. So we have this nice rectangular region right there. So the main purpose of the example we just went through is just to show you a different type of a parameterization. So we're not going to do any calculation actually with this one, but I'm going to use it again to summarize that parameterization we figured out, which is in summary is this: x as a function of s and t, and y as a function of s and t, in such a way all the points inside this triangular region correspond to some point here, and except that around that 0, 0 point, that nothing is pinched or collapsed, and we call it's a one-to-one nice correspondence, and these functions are differentiable and so on. So, like I said before, our main goal is that, okay, first we accomplish that this non-rectangular region is parameterized to, with this S and T, they form a rectangular region. And the next step is that if you take out this tiny piece like this one here, and in terms of delta S and delta T, which is maybe this tiny piece there, how can we kind of approximate, how can we analyze this area, quadrilateral area? The sides happen to be the straight line, but in general it doesn't have to be, because it's very special form of the function makes this edges here, boundary straight line. How are we going to approximate, or how are we going to exactly calculate this one? And that's our goal. And especially not for this one, in general cases. So in general, we're going to have this region has this kind of four sides, and each of the sides is not straight line. So we have to think about the computing some area of a closed region, and we need the following formula. And this is something I do in my Calculus 2 courses in the section about parametric equations and curves, but I'm very sure not many of you are familiar with this type of a formula, so I'm introducing here. So this is happening in xy plane, and we have a parameterization for x and y by one variable there. So that is going to define a parametric curve. So especially we're considering the situation that these parametric equations form a closed curve as t varies from a to b. So we're not looking at the situation that in between this value t and ab, this curve is like self-crossing many times and come back to b here. We're going to assume however you perceive this one is kind of once make this around and come back to this starting position and form this very rather simple looking area here. And we want to compute the area of this enclosed region in there. And especially I indicated here this is something called orientation. So if you look at it as a kind of similar shape of a circle, and we have a notion of, just going this counterclockwise, and so I hope that part's clear. I don't want to go into any more complicated definition of this notion. Let's say we accept that, so going around the counterclockwise orientation. Then here's a theorem. If the curve is oriented counterclockwise, then the area of the enclosed region is this following. gt, let me show you again. Let me change the picture so that we can see about the whole thing. So here's the whole thing. Then gt was the x-coordinate, and ht is the y-coordinate. If you think about how to change the variable and stuff, there's a ht here, so we're integrating y, and what this g prime t dt is really approximating delta x right there. Okay, so if you differentiate this part, dx dt, dx over dt will be g prime of t, and that part is kind of correspond to dx. So I don't want to go through the whole proof of why this one it's correctly measuring the area or anything, but this is the formula. I'm giving you interpretation that ht is this y value, so we're integrating the height of each of the point, and g prime of t dt kind of picks up this delta x part. So it's like y dx form. And this part here, by the way, is a g, so that's x part. So we're integrating x value along with this tiny segment, which is y part, so it's going to be delta y. So let me explain about the sign here. Is that because this counterclockwise is a standard in describing this orientation, if you look at this y part, is you can see that in this part of the curve, y is rising, and in that part of the curve, which is upper limit for integrating over x coordinate, and upper part is x coordinate is decreasing. That is what is causing these sign changes. But this is the formula, by the way, and I'm going to use the pictures to explain more about this formula, and from there you might understand the sign involved in here better. So this is very sloppy, just the outline of the proof of the earlier formula, so I wrote it here again. H was, I had to go back and see, H was y, so we're integrating y value along with, this is pretty much close to dx, the delta x rather. So let me show you this part. When t varies from a to c, so this whole thing varies a to b, but let's just look at this a to c, where this t equals c value is where there, this part, this rightmost x value is attained. So in this orientation, g prime of t is going this way. That means it picks up the positive value there. G prime of t is x coordinate, g of t is x coordinate. So g prime of t in this case, as you can see, as t varies, x coordinate is increasing, therefore this picks up a positive value. So this will be actually from a to c will be the area underneath this curve up to c. From c to b, which is the remaining portion of the integral, you can see x coordinate here is kind of decreasing, you're going to the left. Therefore g prime of t, gt is the x coordinate, is decreasing, so that picks up the negative increment of x part multiplied by y coordinate ht, so that picks up this area with a wrong sign of delta x. So it picks up this area with a negative value. So that's why I wrote like this whole thing. So going, the whole integral is going from here to there, that picks up this positive, and going from c to b, this entire thing is going to be negative region. So opposite sign have make this cancellation happens. So what survive is this part is canceled out. So what's left is here, and especially if it came from this, what left over here, it came from that portion, and that entire thing has a negative sign, so it's going to pick up negative sign. So if you integrate this way, it's going to correctly kind of measure this area of this enclosed region, but it picks up the wrong sign. It's because of this counterclockwise orientation. The next picture here is actually doing with respect to we're integrating along y-axis. I forgot to write it down here, but let me do that. Okay, I quickly added this part here so you can see it. So forget about this one, it came from the earlier part right here. So if you look at this integral, we're integrating gt, which is the x value. So x value goes from here to there. This is where x equals 0. That whole thing is going to be the x value. And h prime of t, h is the y coordinate. So h prime t dt measures pretty much the dy part, the delta y part. So when t, for example, goes from c1 to c2, so that's some intermediate value that makes this rightmost part of the curve. And as you can see, that's the top curve, that's the largest x values there, and it is going up. And therefore, the y value is increasing. So h prime of t picks up this how y value is changing. That must be positive because it's rising in that part. But if you look at the other part, for example, c2 to the terminal point B, or a2, this c1, it's missing, is supposed to be c1 here. For all those parts, you can see as t increases, y value is going down. And this part here is actually supposed to go below a little bit. It's almost vertical, so you don't quite see that it's supposed to go below. So they pick up negative x values here, x values times a negative increment of the y values. Therefore, these two things, as the sum of integrals, have a positive sign of area and negative signed area. So if you add these two as an integral, they cancel and pick up this region which is positive here. So we have two choices of calculating this. Both of them will give a correct magnitude, and since we fixed the orientation of this curve, of this closed curve, why don't we use this part here so that we know it's going to pick up the positive area. So let me show you the formula one more time. We're looking at this closed region, the region enclosed by this closed curve, and the way to calculate the area of this one is integrating this formula gt h prime t, where g is the y coordinate, g is the x coordinate, and h is the y coordinate. And you just integrate along, and it's going to pick up the enclosed area correctly. So we assume, seems like I kind of indicated that everything here is smooth and continuous. If you lose the smoothness, but if it is like piecewise smooth like this, and you can still argue in the same way, and we can still use this formula if this piece is a piecewise smooth. So, which is actually going to be our case. So here's our situation. Then we have certain region here in xy plane is actually the bigger than this, but we're looking at the tiny piece under certain parameterization. Then we have a nice parameterization so that we're going to be looking at this nice small rectangular region in parameter space, but it's going to correspond to this. Now, it's not a parallelogram or any polygon or anything. It is just 4 sides, and each of the sides are possibly curved under this parameterization. So we have to figure out the parametric equation of these 4 sides and do the integral around, and that's going to be exact formulation of the area constructed in this form under this parameterization. So there are various conditions, I wrote it here, to make our technique work. For example, like all the other videos, and I'm assuming partials behave very nicely, so the partial and second order, probably even higher order, I remember when I went through argument, I even have to assume these third partials exist or something. But we have this nicest condition you can imagine, and these are one-to-one parameterization. Unlike the triangular shape that is pinched down in one part, we're just going to assume everything is one-to-one. But if those we call the singularity happens in dimension 1, that doesn't affect the volume of the whole thing. So later it's relaxed, but for the sake of shorter proof, still it's long, but the shorter proof, we can assume everything is one-to-one and there's no pinched transformation or we call it singular points, and I suppose that doesn't happen. The main point is computing in terms of this location of this base point where this one's going, and in terms of delta s and delta t, how much this s and t moved. We're going to calculate this area of this piece fairly accurately. Here's another part that I don't want to be too rigorous about, especially now conditions. We're just going to assume this parameterization have the following property. So we have this tiny piece at a certain location. So this is supposed to be a very small rectangular cell in ST plane. So if you look at the boundary, because of the one-to-one parameterization condition, it's going to look like this. So this is going to be stretched out, not going to flip up or folded or nothing, none of that shape. Everything is going to be just gently stretched around. And if you look at this boundary going around counterclockwise in the ST plane, that should preserve this counterclockwise. Some of the condition we set out earlier will force this condition, but we don't want to go into that argument. We'll just simply assume this parameterization is something we understand, such that counterclockwise boundary parameterization in ST plane correspond to counterclockwise XY plane. So if not, you can certainly switch things around and probably can fix the parameterization such that it has a property. Again, it's going to end up at sign difference as long as we have one-to-one property. So this is not some serious thing that we are not covering. It's just to make our argument clean and easy. We're going to assume this type of condition fixed. So here's the whole picture. So this is where S and T are varying, and this whole picture here is actually taking place in an XY plane. So we have the base point x0, y0, that correspond to s0, t0 over there. And all this corner point that I'm describing in terms of the parameter, not in terms of x and y. So we're going to look at this boundary and then see how this boundary changes, and we look at particularly what are the parameters along this boundary. This boundary came from this horizontal line where t value is fixed. So this has t equal t0, so everywhere here is going to be t equal t0 fixed. So that's why we start from s equal s0 and t equal t0. That's the parameter, and actual xy coordinate is different. And along that line, t is kept to be t0, and s is changing from s0 to s0 plus delta s. And this is the amount delta s. This is what happened to the parameter. So it'll have its own different x and y coordinates. So that point corresponds to this parameter. Next boundary is this vertical boundary in this ST plane. That's where s is fixed and t is varying. So that point has s parameter s0 plus delta s. So along that, t is varying. That's why you see at that point, nothing happened to s part. S is still the same. But t from t0 changed to delta t plus t0. That delta t is how much this guy moved over here. So this part here is where s is changing and t is kept. That's the top horizontal in the ST plane. So t is going to be fixed. So t0 plus delta t is the same over here in this position. And s is changing from s0 plus delta s. But at that position here is the s value there is s0 again. So that must be this s0 position. Then going back has to be this position. So we figured out kind of how the parameter changes along the boundary. So using this x and y parametric equation, we can write down the parametric equation, one variable, sometimes one variable in terms of t, sometimes one variable in terms of s and t, things like that. So if you integrate along like this, four pieces together, that's going to measure the area inside this region. So see that how neat that formula was to compute these things, computing this thing to make accessible. All right, I'm going to simply denote this area of this one by delta A. And first we're going to integrate along this side, which is what s is varying. So that's why the first integral, you see this s. Okay, s is a parameter. And what we are calculating, what we are integrating is x along with the pieces of y. So x is denoted by g, and there's h differentiated with respect to the main parameter here is s. So that's why it's a partial with respect to s is there. So g is the x coordinate, h partial s is the dy part with the parameter ds in there. And since s is varying and along this whole part t is kept t equal t0, so that's why we have t0 and t0 there. So s varies from s0 to s0 plus delta s. Okay? And that part here is going to be this red part where the t value varies. So when t varies here, again, the integrals are always the same. Here's a g, that's the x-coordinate, and here's the delta y part. And because t is varying, the derivative part is going to be with respect to t. So the beginning position, s value is s0 plus delta s, and the terminal position there, s is still s0 plus delta s. Okay? So s doesn't change along this line, along this curve, and t varies. So that's why t and t is there. That's the main parameter, and the other parameters fixed, and then dt there. And t varies from t0 to t0 delta t. Okay? Now we can fit in everything here. So we finished this first two paths. So we're going around. And then third path here is s is varying. So again, g and h differentiated. Since s is varying, that's why we have s differentiated with respect to s. So that beginning point, initial point there, t is t0 plus delta t, and along this path you can see t is still t0 plus delta t. Okay, so they are kept constant like this, and s is varying. This time this position is s0 plus delta s, that's why the initial position has this s0 plus delta s down there, and in here a terminal parameter value is s0, so you have to put s0 there so that we go from here to there. It's kind of a bit awkward, but this is the right thing to do. So look at this part, the same the last bit, the initial position s0 and t0 plus delta t, and s is not changing, only t is changing according to that. So t is the variable here, and s part is fixed to be s0, and here's s0. So along this curve, s is fixed to be s0. So altogether, this must measure the area of this one exactly, not approximation or anything. Now let's see how this is going to organize, and we just finished calculating these two lines, and of course we're going to look at these limits where this is kind of similar. So it's s0 delta s and s0 delta s and s0 and s0. So we usually write s0 below, so we're going to flip this. So if you flip this one, you get the negative sign. So that appeared, exact copy appeared here. And that part appeared there as a negative. The reason I pulled out a negative is because later on it's going to look in this shape. But so that's how I did it. So that part gets a negative. This has the right order of this limit, and because we pulled out a negative, this must have a negative there. So that part is copied exactly there. So we'll do the same thing. So it's exactly the same explanation. So I want you to pause the video, and see if you follow these two things are organized correctly here. Okay? So I hope you find this done correctly. And now if you look at inside, then something common things happening. There's always, because it's all integrated along with the variable s in here, we have s and s and s and s, so that's the main variable. And first part has this t0 delta t and t0 delta t, and the second part has t0 and t0. So something's very common in here. This t value has a common value, and that t value has a common value, and s is common throughout this entire thing. It's the same here, is integrating with respect to t. So t's are all common, but for the first part is a g times ht g times ht, where this s slot has the same function value, and s0 is in here. So it's in a pretty good shape to so that we can apply mean value theorem. All right, let's just focus on this part, and then you can't, let's forget about it and where it came from and stuff. It's kind of difficult to remember everything. Let's just focus on what's written here. So we're going to focus on that part, and we're going to separate this one and rewrite it. All right. So that's written here. The inside the integral to separate it, like I said before, the Sn, 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 they're all common. So you can look at the first term with the function of t, where the t value is a t0 plus delta t. And this has exactly the same form of the function. Sns is the same, only the t slot has a t0. So you can look at this as a function of t, and everything else is fixed. So the following is the application of the mean value theorem. This is a function where t0 plus delta t is applied, and this is the same function where a t equal t0 is applied. The mean value theorem says difference of these two function values is a derivative, special value of a derivative, times difference of input. So input here is a t0 delta t, t0, the difference here is delta t. So that's why we have a delta t out there. And this is a special value of a derivative of a function. The function we're looking at is this function here, where s slot has s in it, and t slot is varying. But in overall form is like the function g times hs, differentiated the main variable with respect to main variable, which is t, so it looks like this. So we're going to apply the product rule there, and then specialize it at this mysterious value t star, and multiply by difference of input t value. So that's why it looks like this. So product rule applied, derivative with respect to t, the gt hs, plus g not differentiated, and the second factor hs differentiated with respect to t. Everywhere there's s, and t spot here is replaced by the special value t star, and multiplied by delta t. So that's how this one is rewritten using mean value theorem. So here's the integral. Let me show you again. This whole integral, what we did is that we sort of rewrite this one as a slightly different form. It's kind of difficult to see what just happened, but it is rewritten slightly different way, where the more partial kicked in. Now we're going to take that portion right there and do the same thing. So this portion is quite similar to what we did over there. So you separate that part and try to use the mean value theorem to one of the variables. So I want you to pause the video and try to do this part yourself, and that's often the best way to follow this type of very technical lectures. So go ahead and try. Okay, this is what I got. If I look at these two functions, you can see all the t's are fixed, just like before. And s slot has this variable s0 plus delta s common, and s0 and s0, and overall is the product of the values of a g and the value of ht, the partial with respect to t. So we can look at this as a function of s. And the mean value theorem gives us slightly different special value, so because it's a completely different integrand that we're looking at, so I use a different symbol, s hat, but overall this is g times ht, and the main variable varying here is s, so it's with respect to s here. So if you apply the product rule to that part, and you're supposed to get this one where the t is all fixed, t is the main fixed variable there, then and there's s hat applied on everywhere, and this is how you get the product rule out. All right, we're back to this thing that we have just calculated using the mean value theorem. This is a typical form of the mean value theorem, so I didn't state it. But next form is a rather integral form of the mean value theorem. So let me formulate that, and I hope you are familiar with this form. All right, this one is what I mean by integral form of the mean value theorem. So if you have an integral from a to b, and this integral where k is a function of one variable function, this integral can be written as this type of a value. You can enter fundamental theorem of calculus and turn this one into an area function and obtain this result. But if you think about intermediate value theorem and how this function value varies from maximum value of k to the minimum value of k, and have to draw pictures of what this left-hand side represent, and you can easily find that there must be some intermediate height that makes this rectangle, area of this rectangle, exactly equal to the area of this integral. So there's no prime here, it's just a ku star. This is the height of a certain rectangle intermediate that makes this area of the rectangle exactly equal to this area. So it's mean value theorem, the fundamental theorem of calculus, somewhat actually uses this property, this version of this mean value theorem. So if we have to prove it, probably better not use that. So what I just described roughly is one way to prove it. But this is a form of the mean value theorem, integral form. Okay, we're back to that calculating area of that piece, and you have to trust me that I copy those part correctly. So let me show you again. So this is the inside of the first integrand. We had that, and using the mean value theorem, and that required us to use the product rule, and we have this shape showed up. So I copied it down there and bring that integral back. So here we are. So that's copied it here. Now we're looking at the integral, and I just stated that if you have two integrals like this, and if you're looking at it as a one variable function, and then you can kind of rewrite it without the integral like that if you have this b minus a attached to it. So let's look at this here. Fortunately, we have all these t stars and t stars, and everything is just a one function in there. Well, even though there's the different values, you can look at still as a one function with all the s in it. So fortunate part is that we have all the s's in here, and this is a function we're looking at, and the delta t is not quite changing with respect to s. Okay, s is a variable, is delta t, and delta s is something we fixed at the beginning of the setting for calculating this delta a, the area there. So this is quite a function in terms of s, and according to this version of the mean value theorem, and it's going to all change to the entire, this is considered as a constant, so all this thing will change to something else like s star. So that's why we used s hat before. So this is going to change to s star, the mean value theorem. That's going to be s star, these two spots as well, and multiply by the difference of these two limits, which is delta s. So it's going to be multiplied there. So I want you to pause the video and write this down yourself, and to get kind of familiar with this. What is that? If you just keep looking at this lots of terms and with a confusing notation like this, and then it's almost impossible sometimes to follow. So try to apply this mean value theorem to this line and compare the answer with mine. So this is the answer I had, and simply that s star is replacing that part. Negative was out there, and delta s was a constant inside. Then you have to multiply that, the difference of the limit of the integral, which is delta s here, so that makes that entire thing, it's written in this form. Now I'm showing you the entire formula of this delta a. We integrated along and then reorganized this s integral and t integral, and we wrote this one using this integral version of the mean value theorem. Now we have to do this one as well, and we're integrating with respect to t, and all this s hat is relative constant here, and delta s is also constant. So pause the video and apply this intermediate mean value, integral version of the mean value theorem to the second term of this version and to compare the answer with mine. So this is the full answer I got. We were working on this line right here, and we already did this one and that one. So delta stays there, and the integral, the mean value theorem says you just replace this one with a t star and multiply by delta t. That's the mean value theorem, not t star in this time here. We're using t hat. So we turn this delta a into this form. So this is good because everything is multiplied by this delta s times delta t. That's promising, so that when we rewrite this entire thing and we have this common factor of delta s and delta t, that's necessary part to write this one as a Riemann sum for s and t. And inside here is a bunch of partial derivative. Okay, so that was there. So this is supposed to be delta, and we're going to reorganize this one to something that kind of is important. So turns out if you compare these two terms, G and HST and HTS, they're kind of exactly the same if we assume that H has a continuous second order partial, which is part of the assumption. So these two things actually, by Clairaut's theorem, these two things are very, very close. And S tilde, S hat and T hat, and S star and T star is almost equal to each other. So these two things are going to be almost canceling each other because of this negative, but these are different. There's probably never, there's a chance that these are canceling each other. So we're going to look at that as a significant part and collect it here. So GSHT with hats, and GTHS, GTH with star. So there's this S and T out there collected. So we have this portion. And rest of the part is collected here. Again, they look exactly the same if you use the Clairaut's theorem, almost the same part. So this one is really, really small. So not only delta S and delta T's are approaching 0, there's another order of a vanishing here. So often when that happens with the Riemann sum, this whole thing contributes as a vanishing part. So only that part matters. So this is non-vanishing part multiplied by this piece that we're kind of measuring against, delta S times delta T. It seems we're very close to finish off this problem, and this is going to be the factor we have to carry. And if you think about the Riemann sum, so here it is. I went back to the beginning of the slides and found the Riemann sum here. We are doing a whole lot of calculation about this delta AKJ. Without this index, we analyze this one. So if you look at that part, this will be obviously replaced by whatever the parametric formula we have G and H there. And this is about to be written in terms of S and T. And what the problem there is that we have two types of special values. We have this S stars and S hat and T star and T hat. That's a little bit of a problem to directly apply the definition of the Riemann sum that requires all same types of special values. So we're back here for that formula of a delta A, and here, as I said, we have this nice delta skj and delta tkj. If we enter to the kjth interval, then this one has these two types of special values, and that has two types of special values, and it's going to be multiplied by f of xy that must have must choose one of the special value, the same here. So how we're going to resolve this one nicely is the following lemma. Let me show you the whole lemma in here. So it says, all right, if you have a function and in the Riemann sum with a one type of a special values, and if you have another function added to it with another type of a special value, all multiplied by this area of the piece here, then it actually, and if g and h are two variable differentiable function, if that, it's actually continuous function is sufficient to guarantee that. But for the tools that we are going to use for our proof here in this level, and if we have this differentiable function, and then we can pull out this fact nicely, but the continuity also works. So let's look at it here, and if so, that the Riemann sum of the G part exists, H part separately along with this piece is multiplied, that exists too. So if you add them together like this, it's going to converge to that. So that's the one lemma we're going to use. And if it is multiplied to each other like this, it's slightly more work to take care of this. So again, we're knowing that these two, G and H, they're integrable, then the product with a slightly different special value will converge just to this integral, double integral, where you might treat as if these two things are almost the same, and that difference is negligible, it turns out. So with this, we can write that estimate of delta A, not estimate, an exact expression of delta A, nicely in terms of integrals. Showing you this formula again, we are about to multiply the function value f in there. Maybe you're going to choose that star for the special values of the function. Then this part has no problem, everything is star, but when f is multiplied to that part, one factor has the star special value, and the other part has a hat special value, and that's where we're going to use the lemma. So I'm going to push the proof of that lemma to the part 2 of this video, and it kind of used the same flavor and techniques that we used earlier in the video in the Fubini's theorem and type stuff. So I'm not going to do it in this part of the video. In the second part of the video I'll do that. But if you believe that, and we can do something about this this portion. Alright, here's how all things are together. Now we analyze this area, little piece delta A, and all this thing is happening for each of the kjth interval. Therefore, we must have those indices. Now this is the original Riemann sum, that delta A kj now will have these terms. And because x and y are parameterized through this g and h function, and all this star value, we're going to use the star value. So each of the star value will have skj star, tkj star in there. So I'm showing you one more line, and that part is just copied it here. Xkj star and Ykj star is actually in terms of star values of S and T. That delta AKJ is replaced by these terms. So there are more lines here I'm not showing, but I'm just taking that one term here multiplied by this delta S and delta T. So that's multiplied to that term. So that's why we have these two delta S and delta J multiplied to GS, partial with respect to S, and HT there. And forgot to put this indices, it's got messy here, but that's exactly this part with indices multiplied by this delta S and T. Now let me show you the whole thing, that, or you might pause the video and do this one yourself, and not that it's hard or anything, that you get by doing this one yourself, you get used to this and easier to follow all this difficult notation. Not difficult, it's just confusing notation. So GT and HS copied it right here with the star values and multiply by this delta S and delta J. This whole thing, I even abbreviated here, all the indices are the same, so I put this dot instead of KJ. All these things are hat values, hat specials, and minus all these things are star values. So star, and it's supposed to be star. It's a typo. Sorry about that. So we have all this Riemann sum. Each of these Riemann sum, when you separate it into 4 different Riemann sum here, they all exist because these are assumed to be continuous. So all the partials assumed to be continuous functions. So we can break this one into 4 parts of the Riemann sum, and they all exist. So again, you might want to pause the video and try to separate all this Riemann sum yourself and try to write it as an integral form. Alright, here's how I did it. This is not going to be exactly equal to this Riemann sum. This is going to be actually, it's going to approach the following Riemann sum. If you look at the first bit with this delta s and delta t multiplied, then this changes to whatever the order you choose by Fubini's theorem. It's going to be okay. Then we have f of xy actually written in terms of s and t, so we understand x and y in terms of s and t. But there is this factor, GSHT, should be multiplied to correctly capture the first term here. And the second term, GTHS, and there's this ST pieces, and GHTS, and here's GHTS, I forgot to write F first there, but F can go in the front place. The last bit is a GHST, and GHST there. So this might be the last bit of the video of a part 1. So if you look at this formulation, that Riemann sum is supposed to approach this value, and that value is just there. But if you look at the second line, then GHTS and GHST, that's the only difference between these two functions. And by Clairaut's theorem, these two is continuous function, and they are equal to each other. Therefore, this integral is exactly equal, and that becomes just flat 0. So that whole value must be approaching this integral. What I did for that one, because it has this f and f is common and the same limit for this iterated integral, so you can bring them inside and factor out f of x. So we formulate it in this way. But we recognize this one as the Jacobian of this parameterization. So I better show the meaning of this Jacobian, and then that's going to be end of it. End of this part of the video. Right, I just created this additional slide, and this was our final answer, that Riemann sum is approaching this integral value. So this is the height of the function. As we rewrite this delta a piece, and in terms of delta s times delta t, there is a stretch factor kicks in. The interpretation of this one is actually this piece here is the determinant of the matrix, with the first column being GSHS and second column being GTHT. So this delta a piece is quite small relative to actual velocity vector. So GH is actual position vector. We, in terms of S and T, we parameterize the position of xy using this function g and h. So it's some sort of derivative, so that must be some sort of velocity vector. Along the S is along the S curve, and if you differentiate it with respect to t, that would be the velocity vector along this t curve. So at that given point, these vectors is actually very large compared to this tiny size delta a. But in the formula, the Riemann sum formula actually is multiplied by this delta t and delta s. So it actually turns out this whole thing, not just this proportion factor, this whole thing is comparable to the following thing. And this is the vector that is parallel to this velocity vector, scale back down to delta t, and this entire thing is the longer velocity vector scale back down to this using this delta s. These are small quantities. So if you compute the determinant of these two scale down velocity vectors, and that's correctly measuring, kind of approximating this area there. So what is this determinant? Is determinant of 2 by 2 matrix is the same as the volume of the parallelogram formed by these two sides being the first column and the second column. So this parallelogram, this is not a 3D picture, it's all happening in XY plane. This A piece is a slightly different shape, but if you use this parallelogram coming out of this tangent vectors shrunk down to that part, and this parallelogram is a correct approximation of this delta A, so that when we replace that area with this factor here, it correctly captures the value of the double integrals. So that's one explanation of why that Jacobian factorizes that way. Once you discover the meaning and the determinant interpretation, it kind of makes sense, but that can never be correct proof of justifying that factor is going to do it. So we have to really look at carefully. And in that process, we use this lemma that the Riemann sum of different special values can be just treated as a Riemann sum with the same special value here. And the proof of this one, it's fairly technical, but use the same method we use for Clairaut's theorem and Fubini's theorem, and it's going to continue in a part 2. Thanks.